My name is Pedro. I work at social games company, and we do all our analytics stuff using Hadoop. And we also don't have any real infrastructure, so we run it on Amazon Elastic MapReduce. And I'm here to show you how we handle running Hadoop jobs in Perl as opposed to the native Java API. Sorry, but this thing doesn't work. So most of you probably have heard of MapReduce, which is a distributed computing model. Basically, the work is divided among several machines and several processes running on each machine. And it's a two-step, two-phase processing. So the first phase is the mappers, which get all the raw input, do some processing on it. Forward the results to the reducers. The reducers aggregate the output of the mappers, do some more processing, and then finally write out the final result of your processing. And it's basically this. There's that sort phase in the middle, which is handled by the framework. And that's very important. That guarantees that all the values emitted for a single key by the mappers are sent to a single reducer. So a reducer will get all the values for a given key, so you're guaranteed that you won't have any more values related to that key elsewhere. So basically, mappers get the input as key value pairs. They emit key value pairs as their output. These are then sorted by the framework and sent across the cluster to the reducers. And as I said before, the sorting guarantees that a single key is sent to a single reducer, and all the values for that key are sent to that reducer. And the reducers get a key, they get key value pairs, but the key is the key that the mapper output, and then the value is a list of all the values output by the mappers. Once they do their job on this data, they emit a final key value pair, which is the result of your computation. As a short example, we wanted to have a world map. I'm sure you've heard of Mozilla Glow, which was this thing that Mozilla put up when they launched Firefox 4, and it showed downloads in near real time on a world map. We wanted to have the same thing every time someone started one of our games on Facebook. So we took Mozilla Glow, which is quite nice, and we decided to build on it. And we ended up with something like this. This was supposed to be a movie, but Windows won't play it, so imagine that those lights are going on and off. So basically, every time a player or a person starts a game on Facebook, you get little flashy lights. We did the same for sales in different games, but I'm not going to show you those. But you can have different colors, and it looks pretty, and we like to show it to people who go into the office. So we wanted to do this, but we wanted to do this in a day. So the input for this, we have game start events, and we have the epoch for the event, and we have a payload in which there is an IP address. So to do this, the mappers would group the events in 5-minute blocks and output a block ID and an IP address. The reducer would get the block ID and then all the IP addresses that happened, that started the game inside that 5-minute block. They then did a geo lookup and emit as the final value some. This is simplified because this is a JSON structure, which is what Glow uses. So basically, we emit the epoch corresponding to the block ID, and then all pairs of latitude, longitude that happen in depth. Again, it's just basically doing this. And we did this in Hadoop. So MapReduce was a paper that Google put out a few years ago. And they have their own MapReduce implementation, which obviously isn't public. And Yahoo started Hadoop several years ago implementing MapReduce, and they've transferred it to the Apache Software Foundation, and it's open source. What is it? It's basically a distributed programming framework which implements MapReduce, but most importantly, it does all the distributed programming thing, like data serialization, heartbeat checking, node management, directory services, assigning tasks to nodes, etc. It's highly fault tolerant. If a machine dies or a thread that's carrying out a task dies, it just takes it out of a cluster, reassigns tasks as needed. It does something they call speculative task execution. So they send a task to several machines. The first one to finish it wins, and then it just tells the others to stop working on it. So you don't need to worry about any of that crap, and you just focus on your business logic, on the mappers and the reducers. Hadoop comes with a native Java API. So obviously you can write your MapReduce code in Java, but you don't usually have a pile of enterprise Java architects around. So this Hadoop comes with a streaming API, and you can write mappers and reducers in any language you want, even Bash if you want so. It also provides a distributed file system, HDFS, which is so every node is part of HDFS. Every file you store in HDFS is replicated and is available on all nodes, although not at the operating system level. So the operating system doesn't see HDFS, only Hadoop does. And it also provides a distributed cache, which again is replicated across the cluster and is seen by the operating system. Amazon's Elastic MapReduce is a basically on-demand Hadoop clusters running on EC2. They have so Hadoop supports S3 as a file system, but Amazon obviously did some work on it, and their distribution of Hadoop has much better S3 support than the standard ones. And also, I think that their Hadoop instances are really close to S3. So you can use S3 for input and output data, which is quite handy because it's virtually infinite storage and highly redundant. And you just build workflows by sending jobs to the cluster. Amazon calls jobs steps, and they call a cluster a job flow, which is sort of misleading. S3 performance is quite good. We got around 750 megabytes per second, which for our average event means that we get 7 million events a second into the cluster when reading the input. So that's more than we need. So there are downsides to it. Unlike other EC2 instances where you can choose the machine image to use and you can customize it and all that, you have absolutely no control over the machine images. They're fully controlled by Amazon, and you can't clone them and do modifications, etc. They come with Parallel 588. If the cluster dies, and the clusters, EMR clusters die much more frequently than EC2 instances, I don't know why. They're designed to be ephemeral, so you don't want to store your data on HDFS. because when the cluster dies, HDFS is gone and all the data is gone. HDFS is not available when the cluster is created, which means that you can't store, when you start a cluster, you can't store things in HDFS to make them available. And finally, it's Debian, which I don't like. So, streaming, the streaming API, it's basically you do a cut before doing all the rest. And instead of getting a key and a single key and then a list of values, the reducers actually get a key value pair, so the keys are repeated in streaming jobs. But everything is sorted, both the keys and the values. So for instance, if you wanted to merge 3 tables, all you have to do is set, so the user ID there is the key, and then you just have a merge field, and if you set it to 0, then you know that that's going to be the first one you'll see for that user ID. If you set it to 1, that's going to be the second one you see for that user ID, and so on and so forth. And when the user ID changes, when the user ID changes, you know you have a new user, and you'll never see that user ID again. Streaming has a limited API. You don't have access to all the goodies of the native Java API. You can't set the same job parameters that you can in the native API. It's a bit slower to run, but it's much faster to write code for. So instead of writing 3,000 lines of Java, you write 100 lines of Perl or Bash or whatever, and it gets the job done much quicker. So you can't forget about the 10% increase in runtime. The problems with streaming, tasks started by Hadoop run change rooted, and you don't know where they will be. It's very easy to get files into HDFS when you submit a job, but you can't store directory trees on job submission. For native Java, you just get all your dependencies in the jar file with your mapper and reducer classes, and that's it. It's not true in Perl. So you have to define your inputs and your outputs with the streaming API has a lot of niceties to make your life easier. So you define your output, you point to S3, to a bucket, input and output. They can be different buckets. You can use different access keys for the buckets. For instance, for the input, you can only have read-only access, and then you have a bucket where you have read-write access. Even in streaming jobs, any class that's in Hadoop's class path can be used as a codec to read data or write data out. So you basically just have to choose from one of the classes. This one is one of the most used, key field-based partitioner, which is a tab-separated values, basically, and the first index 0 is the key, and the rest of the line is the value. And then you use S3 to store everything. So input data, output data, any databases that you might need, and most importantly, your code, which gets stuck in S3. And this is how you specify the mapper and the reducer. So you write them, stick them on S3, and when you submit a job, you define it like that. You define them like that. Now we have to make use of the distributed cache. So for instance, for that problem before, we needed to have the GeoIP database available to every node in the cluster. So there's a cache file, switch tells how to get this file and put it in distributed cache. And then you give it a fragment, and what Hadoop does with this. So remember that we don't know where this thing is running. But if you give it a fragment, Hadoop will create a symlink in the current working directory of the task to wherever it puts that file. So you can access it as if it was available locally. And if you start an archive, it does something even cooler. You specify a fragment, and what Hadoop does, it will uncompress the archive and create a symlink to that directory, wherever that is. So basically, this is the way to get your Perl dependencies available to the job if they're not available in the standard library. Because your mapper and reducer are also stored in the same location, and basically you just have to use lib.
You could put a whole binary there. You could ship your own Perl.
No, you don't want to do that. It's too much work.
Okay.
We can talk about it later. So basically, this is a mapper for that world map thing. It's just this. So there's the uselib. It's using JSON-TP, and basically what it's doing here is just getting the epoch and the payload, and the payload will be field 5, the JSON payload of the event. Our events have several fields. Hadoop has this really cool thing, which are counters, so you can count stuff, and you're counting these on all nodes across the cluster, right? And at the end of the job, Hadoop will aggregate the counters from all tasks and will give them to you, as aggregated values, which is quite handy to count errors, records processed, etc. The reducer is a bit bigger, and there's lots of crap that's not in here. But basically, again, you just use lib. As you can see, I'm opening GeoLightCity that as if it was on my current working directory. Just initializing some counters that I want to have at the end of the job. Again, just checking for if some malformed data was made it this far, and just updating a counter. Here you check. So if the time slot I'm in is not the same time, it's not the previous time slot, then there is it's a new one. So I'm going to write out the results from the previous time slot. Again, this is more counter stuff, more counter errors, and there's some code there that's just updating the data structure where the time slots are stored. Just stick the latitude and longitude in there, and then switch the time slot. And finally, this is because of the JSON that Glow expects. We just emit the last record at the end, and then all the job counters that well, yeah. So, quick recap. So EMR clusters will disappear. You can't rely on them for storage of long-term data. They will go away, and your data will go away. So use S3 for storing important data that you want to have around. All the values for a given key will go to a single reducer, and they will be sorted. Use S3 for everything, and plan ahead how you're going to store your data in S3 and how you're going to get it there. Because if you store it in a path like this, there's a thing called Hive, which I don't know if you've heard about, but it's basically a data warehouse built on top of Hadoop that you query using an SQL-like language, which gets compiled into a MapReduce job, which then gets sent across the cluster. If you have your data with things like this, Hadoop will be able to partition it by this string, by run date. So you can then query Hive, just for instance, just for this date. And it will be much faster because it won't scan other data, it will just look in that directory. your data is in S3, but eventually you want it to end in some database or business intelligence software. Don't worry about getting it out on your main job. Just write to S3, and at the end of your workflow, you can just write a simple job that just reads the data from S3 and pipes it into whatever database or whatever location you want to have your data in. Carton, which is quite recent, but which I'm using enthusiastically, makes this much easier, because you can. I call it shipwright for humans because it is, for me at least, it is shipwright for humans. So it reads dependencies from Makefile.pl. So when you write your mapper and your reducer and the models that will support them, you just write the Makefile.pl, and as usual, Carton will read the dependencies from there, figure out their dependencies, etc., and will install them locally to your app. You then just have to deploy it, including the Carton log file, run carton install -- deployment, and that will install everything, install all the dependencies, and then you just make a tarball of that and stick it on S3, and that's it. Yeah, that's it. I'll be putting this up later on, and I'll slide with URLs for EMR things and Amazon Hadoop things.
Where will you put that?
So, yeah.
Where will you put it?
Slide share.
Okay. Great. Thank you.
Thank you.